push that rock with some math. So we're going to define exponential functions. Exponential functions have a base. Remember, we have another word for that called a common ratio when it was used in a geometric sequence. But it has a base. A base is a positive number, and it can be any positive number except 1. So it can be fractions like 1/2. It could be whole numbers like 2. It can be Euler's number. In fact, that's called the natural base, Euler's number. So it can be irrational numbers like the square root of 2 or Euler's number or pi. So it can be any number that's positive as long as it's not 1. And we might have some coefficients on the x variable and some coefficients out front, or it might simply be something that's just a straight base with the exponent. This would be the doubling function. You put in every whole number doubles the previous output, but it doesn't just admit whole numbers, it'll admit any real number. So the domain of exponential functions is all real numbers, unless you come across them in some context, like maybe in science. And then in that context, there may be a restriction on the domain. But mathematically, you can put any number in for x. That's one of the things we were building up to as a takeaway last week when we used those Taylor series polynomials to evaluate the mystery base. That we can put in any number, a rational number, an irrational number, any real number for x, and it has sense. Because remember, this was that Taylor series. The definition of 2 to the x was 1 plus the natural log of 2 over 1 factorial x to the 1 plus the natural log of 2 squared over 2 factorial x squared, and so forth and so on. And we can put in any number and square it and multiply it by another number. This would simplify to a number. So any number is allowed. Now the natural exponential function uses Euler's number as the base. So this is considered the natural exponential function, okay? And in science and statistics, this function is used quite a bit. And in fact, you have a project this weekend where you are going to use this exponential function, but it will have some parameters. So, maybe have a number up front and some numbers up here, coefficients. So let's talk about these types of functions. So I have the natural exponential function here, and I've created a table just using the integer values. When you put in -3, remember this is about 2.7. So 2.7 to the -3 would be 1 over 2.7 cubed when you put in -3. E to the -3 is approximately this. Well, that's going to be really small. In fact, it's 0.05. It's a little bit smaller than a value of a nickel. So it's really close to the x-axis. And when I put in -2, I get 0.14. When I put in -1, I get slightly bigger than a third. These two I get on a calculator. This one I can rationalize out. I mean, it's e to the -1. It would be 1 over 2.7. Okay, so, it's smaller than a half, but bigger than a third, so about 0.37. Anytime you raise any base that's not 0 to the 0 power, you get 1. So e to the 0 is 1. So at 0, it goes through 1. When you put in 1, of course, e is 2.718. So e to the 1 is 2.718 about. That's the approximation of e. If you square 2.718, you're going to get about 7.4. And if you cube 2.718, you get about 20. 20 is off my scale here. So I didn't actually put that on here. So the graph ends up looking, if I put negatives in out here, like if I did -4, it'd get even closer to 0. So it starts hugging the x-axis. Oh, so there's a horizontal asymptote on the left side. It's only on the left end of y equals 0, only on the left end. Now, if we reflected it, it might be over here on the right end, but it's only on one end of the polynomial. The other end of the polynomial is going to go to infinity, or maybe negative infinity if we reflected it down. But anyway, this is what the graph looks like. These are sometimes called J curves. Because of the, I shouldn't have put that top maybe, but because of the J shape. So this flattens though. So this is sometimes called a J curve, and the exponential growth gets very dramatic. And so in layman's terms, when people want to talk about something growing fast, they'll use the word exponential growth. And mathematicians will sometimes cringe because it's not actual exponential growth, even though it may be dramatic. Okay. Now, let's talk about the parameters that might appear. You might have a coefficient on the exponential function. Well, that just dilates it vertically, pulling the xy points away from the x-axis. So if I put a 2 in front of it, all of these points would be slightly higher. This would be up here at 2. This would be, double 2.718, so you're going to be above 5. And double this. So it's the same shape, just all the points are pulled away from the x-axis. That's one thing that can happen. If you put a negative out front, well, it reflects it down, so the graph will look like an upside down J curve, something like that. If you put a coefficient up here, like 2 or 1/2, well, then that's horizontal dilation, or stretching, shrinking, maybe is a better terminology. But what it does is, if this number is bigger than 1, it pulls points to the y-axis. And if it's smaller than 1, it pulls points away from the y-axis. So it just changes the shape, makes it slightly different, but it's still a J curve. Now, e to the negative x reflects over the y-axis. So instead of going up like this, it'll be coming down and look like, well, I should go through 1. Sorry, I almost missed it. And look something like that. Now, interestingly, though, this negative means you can flip the base and make the exponent positive. So this tells us whenever the base is a proper fraction, in other words, the denominator is larger than the numerator, then the graph is a decreasing function. Yes, and in that case, we call it exponential decay instead of exponential growth. And in fact, your project this weekend deals with exponential decay. So either your base will be 1 over e, or you will have a negative coefficient. I think I wrote it with a negative coefficient. So whenever there's a negative coefficient up here and you have e as your base, that means you have a exponential curve that's decreasing. So you have what's called exponential decay, rapid decay. Math made simple. It's Simpson Math.